All right, I got a couple of questions for you guys. When we last met, we were talking about the OSI model. Can anybody tell me what organization is responsible for developing this model? Is that you are? Do you guys want to start with easier questions Monday morning? What's that? ISO, yes, ISO. Now, what's nice about that is the letters are still in the OSI, right? They're just flipped over. So it's a nice way to remember that. And why would the International Standards Organization develop this model? I mean, they create other models. They create other standards for us to follow. Why would they develop the OSI model? Yeah, the idea is that we can foster competition, but yet still keep compatibility. So we have the difference between proprietary protocols and open protocols, correct? And so you can still have proprietary protocols, but what that means is that the corporation owns them, and they're the only ones allowed to change them, and if you want to use them, you have to license them. But open protocols is, we're going to create the standard, you're allowed to look at them, you can modify them, but you have to create a variation of it, like the 802.11n or the 802.11b. They're still using the core standard, right? But then somebody has enhanced it, so they went to n. So it fosters competition, but more importantly, it allows me to know when I go shopping what to look for to make sure that they're compliant. Like when I buy a USB hard drive, I should expect on my home computer that there is a port that accepts that USB hard drive. And back in the day, it was always a nightmare because we had different ports on the back of the computer. And it was like, okay, this one plugs in this one, this goes to that one. And somebody said, this is just stupid. Why don't we have one universal port that accepts everything? And once again, that's starting to grow again. We have Thunderbolt, we have FireWire, we have USB. So it's like, why can't we just have one that rules them all? So standards allow me to know that when I go shopping, the devices I buy are going to be compliant. I threw out the 802.11. That's an example of another standard. But it's a wireless standard, yes. But what organization is responsible for that? They're also responsible for this one. Now, it's always interchangeable because you guys know this 802.11 as Wi-Fi, right? And you know this one as probably fast Ethernet is what I should put in there. What's that? IEEE. For some reason, Cisco in this curriculum is all gung-ho about you guys knowing these organizations. I don't understand why. Other than when you become a network engineer. Now you're getting down to the nitty-gritty. You might be developing new interface cards. But you'll have to look at what we call RFCs. Anybody tell me what RFCs is short for? Yes, request for comments. And it's not read the, you guys. RFCs, request for comments. And how does that system work? Remember, we're talking about open platform, right? So you guys can go to the IEEE site, read over the 802.3 or the 802.11, and start publishing your own variation. Or maybe fix a bug, and hence you're posting the RFCs. And so you're looking at the RFCs as ways to see what's going on in industry. So I guess that's the only kind of BS excuse I can give you why Cisco is jamming down these organizations down your throat. What's the other one that sort of fosters the open platform for the internet? It's more of a society thing. I'll give you a hint. ISOC or ISOS, the Internet Society. And their whole big deal is to try to keep things open and keep the internet growing and people sharing. Okay? So we have the OSI model that's developed by the ISO. And what is the whole purpose of this? Well, we said it's to foster competition, but it also helps delegate responsibilities. And it also can be used to understand the communication process. And that's where we were at last week, right? Dissecting the communication process from the sender to the receiver. What's the first layer, the upper layer of the OSI model? Application. This is also known as layer what? What happens here? What's the responsibilities? If you were to designate, you have a big corporation, you're designating some people jobs, and you're saying, okay, I want X number of people to do layer 7. What kind of skills are you looking for a layer 7 job description to have? Okay, so you're looking at programming skills. These are people that develop applications, design web pages, and nowadays we're just calling them web apps, right? But in any case, we're just trying to say that these are our software engineers. These are people that write code. And what does applications do for us? They give our computers purpose. You good with that? So the application layer acts as an interface to the network. If you are writing code or developing software that uses a network connection, like for instance, if you are developing a web browser, it's always good to have these examples. So if you're designing a web browser, not a web page, but a web browser, what protocol do you need to agree to so that your application understands this process? What's that? HTTP. So HTTP is an example of an application layer protocol. And there's a slew of others, like DNS, FTP, POP, SMTP, and we'll get into those as the semester progresses. Like I said, lab for this week, you guys are going to be getting into HTTP and DNS. Now, when I say they're application layer protocols, I'm saying their responsibility is to work with the user to prepare the data to be ready for the network. And so the OSI model is interconnected layers. It's going to encapsulate things as it goes down. So here I am at the application layer. I'm using a web browser, and that stuff that I'm asking for or I'm sending via my web browser gets passed down to the layer 6. What is the name of this layer? What are the 3 responsibilities for this layer? What's it going to do with that HTTP stuff? It's going to encode it. It might use ASCII to accomplish that. Encrypting, which it might use what? SSL or TCL. The list goes on and on. In fact, this is a huge growing field. If you guys are looking to make a lot of money with a very little bit of education, you want to go into security. Try to get a number of security courses you possibly can get. And if you're really good at it and you're really fascinated about it and have great math skills, in cryptography is the area to go. Trying to create code that can't be cracked. And right now the NSA is bragging that they can crack every encryption method out there in a couple of seconds. So what does that mean? They're going to hire more cryptographers to create code that they can't crack. Because if they can't crack it, then they can feel it's safe communication. All right? A big growing area. What's the third? Compression. Yeah, they want to make this stuff smaller so it takes less bandwidth to deliver it, if you will. All right, and so an example of compression I believe I gave you guys was like gzip, but this stuff goes on and on and on. What's the next layer? And don't get cute and say layer 5. Now, eventually, I will get lazy, and I'll say that stuff happens at the layer 3, and then you need to say, oh, that's the, all right? So here I am, layer 5, and we called it the session layer. If I had to roll that all up in one word, it's just going to be management, dialogue management. It's going to keep your connections alive. That's it. All right, so I'm saying keeping connections alive. See, the application layer, you, the user, could be using multiple applications all at once. That requires the internet. You could have your email program going on. You could have your torrent stuff going on. You could have your web browser going on. And what gets really interesting is with even those applications, there could be other connections. Like, for instance, if you're browsing the web and you're watching a video, and you could also be using email, which we call webmail, and you could also be using DNS, ironically. So just within one connection, we can have multiple other connections. I mean, when we talk about HTTP, we're only talking about HTML and a generic web page. But that has evolved. We're on Web 2.0. So we have plugins, which are going to be at the presentation layer, that's designed to sort of work with the browser and the content provider. Does that make sense? And the way we do that is by establishing separate connections to each of those services. And that's where this layer comes in. Anybody tell me what the layer 4 transport layer? Do not think transport as being this. You take a bottle and you move it over here to its final destination. That's not what we're referring to at the transport layer. Its job, its responsibility, is to get the segment to the right application or service. Now, when I say application, you guys need to think client. When I say service, you need to think server. There's a symbiotic relationship between client and servers. Clients make the request, servers try to fulfill that request. So clients use applications, servers use services. Services are applications. They just are designed to run in the background. If you're a Linux person, what do you call services? Daemons. Got its name because they're running in the background, taking over the server. Right? Fulfilling a role. So if you are running a Linux web server, you might have Tomcat or Apache web service running in the background, and it's listening. It's listening to a particular port. Now I said Apache, I said web server, right? Web services. What port is this server going to be listening to? What number or what address is it going to be listening to? Port 80. Port 80 is the default port for web delivery. So on my server, obviously, if it's going to be accessed from the public, it's going to have a connection to it. But inside this server, I could have different services running. So this server needs some kind of mechanism to identify what the communication is. So when a message comes in here, this server's transport layer is going to be looking for the destination port address. And if that port address is 80, and this service is configured to listen to port 80, the transport layer will now deliver or transport the message to the right service. So you see where the name came from? Not about picking it up from one source and sending it to the receiver. That's another layer. What it's about is when the message gets to the server, what service on the server needs it. So think about it as software delivery. Okay? How does it accomplish that? How does the server know to look for port 80? Is that the header? See, at this point in time, we have generated data. And the transport layer is going to take that data and break it up. When we break it up, what do we call it? And that's what the PDU is for the transport layer. That happens, guys. Let me know if I misspell something. All right. So the transport layer is going to take the data and it's going to segment. We call this segmentation. Why? Why take something that makes sense and rip it all into a bunch of pieces? I mean, if I deliver this all crumpled up, I can do this. And I say to you guys, here it is. See if this makes sense to you. Doesn't it take all this extra time? Doesn't it seem like it's wasteful that I'm just taking that message and ripping it up into tiny pieces just so that somebody can have fun gluing it back together? Why would you do a thing like that? You notice I broke it up and just threw it to different people in this classroom? But that's only one page. I got a whole bunch more. Anybody want to have some fun? It seems like the segment later could do something else with its time instead of just ripping my data apart. That's one. We don't depend on one and only one way out of the classroom. So if one piece gets lost, we have the other stuff to work with. Now that can work sometimes, but that might not work other times. Like what if that piece that I lose is the end of my file? Am I going to be able to open up my file? I'm going to get like an EOF problem, end of file problem. But that would be wasteful. We only have bandwidth that's only so much, so it wouldn't make sense to be sending multiple copies of them all over the place. It's got to have some kind of system of checking to see if things got there. We call this reliable delivery. In order to ensure that we have reliable delivery, we need to also make sure that what? If I'm taking these pieces and throwing them all over the place, it's quite possible that maybe the end is going to get there before the beginning. So what do I need to do about that? This layer, if it's going to rip it apart, better glue it back together, but also better glue it back together in order. So it makes sense for the application layer to be able to display it to me. Otherwise, it's like taking a jigsaw puzzle and just jamming the pieces together and say, I put it together. Well, it looks like crap. The objective is to put it together so it still looks like the picture that you're working with. We good? So we get sort of efficiency in the fact that the messages are dispersed over multiple connections, multiple pathways. Why do I say sort of efficiency? Well, we lose some by breaking it up, right? Because we've got to add all this other stuff to keep track of it. But we gain it because we're saying, if I had multiple ways out of this classroom, and everybody wants to get out of here in a hurry, a few go there, a few go there, a few go there, correct? Just like the difference between 17 and what, 352? One's a 4-lane highway, the other one's a 2. The other thing is sort of security. How many people take the same way to work or the same way to class all the time from home? If you guys have a stalker, you just made my life a lot easier. You just became predictable. So if we're not encrypting the data, it's like a big corporation covering their assets. Just ask NASA, they're known for this. The person making the handle for the door doesn't know what door it belongs to and what project it's part of. They're making one little part, a piece, to the larger puzzle. So it sort of builds security in there because you don't know what the left hand's doing. So you guys can't collaborate and try to, sell the ideas to another company. Likewise, if we send our segments all over the place, it makes it harder for one person to get the whole entire message. But isn't that the intent? For the server to get the message? So now we need to identify who gets the whole entire message. That's another layer, that's another responsibility. Right now, I'm talking about managing the data so that it can get there in its entirety. Transport layer. Does all communications need to be reliable? That's saying reliable, though. So does all communications process need to be reliable? I really blank my job. Could you fill in that blank? You could try. What if I said I'm on the phone with you guys, and we're talking about meeting, I don't know, to go to dinner, or for a movie, and we say, okay, well, I'll be available at 6:30, and all you hear is at 6:30. We already made plans that we're going to go to the movies, but we didn't know what time, right? Because you heard, well, let's plan on going to the movies. Well, what time would you like to go to the movies? And then all of a sudden I'm answering back to you, I say, I will be available at 6:30, but all you hear is at 6:30. Could you say, oh, I guess he's available at 6:30? What if it didn't come in there and all you heard was I'll be available at? Would that work? But it's the same communication, right? We're talking about going to the movies. I can't switch between reliable delivery and unreliable delivery. It's either going to be one or the other. Either you want me to make sure everything got there, or you don't. You want me to stay out of this conversation so that the conversation is lean and mean, more efficient. So, as a programmer, I'm going to decide what protocols my communication, my application, are going to use. If I'm developing a web browser, I'm going to require that I use the TCP protocol of the transport layer. TCP is short for Transmission Control Protocol. It ensures same order delivery, reliable communications. No problem. So we said same order delivery, reliable communication, and develops a mechanism to detect when things fail and to regain those. We call this flow control. Remember we were talking about flow control where a server can get inundated with too much information or a client can get inundated so it starts dropping things? So TCP has a mechanism to control how much segments it's going to be sending out. So it doesn't overwhelm the receiving person. But in order for TCP to do that, what's going to happen is it's going to take part of that data and it's going to slap a header on there. And that header is going to be pretty massive. Sometimes it might even be bigger than the data that you send. And in that header, they're going to have what they call sequence numbers. We call these fields. It's going to have acknowledgement numbers. See, the sequence numbers are like little tags that we know, okay, you got part 1, you got part 2, you got part 3. The acknowledgement numbers are a way for the server to tell them which one it has received or what it expects to receive next, acknowledging what it's already came in. All right, what else? Well, we need to be able to put these things back together, so the sequence numbers help, but we also need to identify what service or what application is using it. So there's going to be port addresses in this header. And that's the only kind of fields that we need to know at this particular moment. There's going to be a source port and a destination port address. The source port is randomly assigned by the client's operating system. By definition, the client is the one sending the data in this communication, okay? So the sender's operating system is going to randomly assign a port address. Why would the operating system be responsible for randomly assigning port addresses for the source and only the source? Well, we talk about using a web browser, right? In this example, is Internet Explorer the only web browser out there? Thank God. So there are certain applications or websites that require you to use that awful web browser, correct? So it could be possible you guys could have multiple web browsers on your computer running at the same time that understand port 80 or HTTP, but when I click in Internet Explorer, I don't want that page to reappear in Firefox. Otherwise, every time I click on things, I'm going to be wondering where the hell did it go in my computer. So the operating system will stamp some identifier to the application that started the communication process. So web browser doesn't have to have port 80 as the source address. None of them will. It's going to be any number over 1024. It's going to be randomly assigned up to 65,535. Yes, you will have to know these addresses, not all 65,000 of them, but the ranges. We'll get into that when we get to the transport layer. All this is a grand overview. So when I have multiple web browsers, I'll be randomly assigning the source port. What about the destination port? I cannot randomly assign that. If I'm using HTTP, I'll be putting in port 80 here for the destination. So this way, my server knows what to look for and what to grab from their resources. Good there? All right. What if our communication process doesn't want all this extra overhang? Adding all these fields, keeping track of things, controlling the flow. What if I throw it out there, like I'm doing today? I didn't say, David, did you just get that? Did you understand what I said? Tony, did you get that? Did you understand what I said? Dominic, did you get that? No, you didn't get it? Okay, so let me say this again. So the destination port is going to be port 80. Do you see how long it would take me to accomplish a lecture in this class if I tried to verify every single one of you, making sure you understand that? Would your education be improved? Yeah, because I'm not letting you guys go. I'm making sure that you get it, and I will drill it until you say, acknowledged. And sometimes that might take me months to do. And we only scraped the first chapter. But you guys are going to be experts in the first chapter. Do I do that in this class? No. I use unreliable delivery. Unreliable? That's got to be awful. Seems to be working for the last couple of centuries. Most of the time that we're lecturing, we're using unreliable delivery. Most of the time, people just like hearing themselves talk. They don't care whether you guys get the material or not. So an unreliable delivery, the transport layer uses another protocol called UDP, User Datagram Protocol. And in that protocol, we want to be really simple. We want to send as much of the data as possible. We're still going to segment it, okay, guys? We're still going to segment it. But the size of my segments might be a little bit bigger than in TCP. We good there? That allows me to send more data at a single time, which should make the process more effective. So I'm not wasting it by resending it. I'm not wasting it by creating all the overhead. I'm just saying, I'm going to send it to you guys, and if you don't get it, what are you supposed to do? Raise your hand, right? Let me know. That's instructions. I'm telling you guys. That's the application. So if I choose to use UDP, and I choose to say that this conversation is either important or not important, if it is, and I want as quick as possible delivery method, then I'm going to build up in here ways of checking the data myself. And that's what uTorrent does. I mean, after all, in order for you to successfully download a file off of uTorrent, you need all the bits from the beginning to the end. But it would take uTorrent a very long time. Every time they send 5 bits, did you guys get those last 5 bits? Yep. Send the next 5. All right, send the next 5. Did you guys get those next 5? Yep. Send the next 5. All right, send the next 5. So uTorrent's like, you know what? Send it. Send it out of order. So when you guys are watching your little progress bar, you might see certain areas filling in. It doesn't go from beginning to end. Unlike when you download a file using a web browser. You know, like on Blackboard, you click on a link like packet trace and you download it. Doesn't that start at the beginning and work its way to the end as progression? Because HTTP uses TCP. And it takes it a lot longer, but ensures that every piece got there, than UDP. So examples of UDP delivery is videos. Videos and audio. Why are those two the prime examples? They don't have to be, but they are. The massiveness, and you need it as close to real time as possible. Otherwise, if I was having a conversation or if I was watching with a video using TCP, every frame I get, it's going to want to verify it. So I'm watching one frame and there's a lag, and another frame and then there's a lag, and then another frame. Or I'm having a conversation with you and it says, hi, my name is, and that's going to take a long time to get there. So anything that's really time sensitive, you need to use UDP. The other thing is, let's think about videos and conversations, vocal conversations. You know, ideally a video is about 30 frames per second. That means every frame is only about 1/30 of a second. And your eye can detect that. Anything beyond that, your eye can't. But a whole length movie could have billions of frames. Are you going to be too upset that you lost one frame out of a billion? No. But what happens if you start losing more of those frames? Yeah, you just you grab that little status bar and drag it back and let it rebuffer. And that's why we buffer. You ever also notice that certain parts of the movie will load up faster when you're streaming it over the internet than other parts? Because remember, we break it out in segments. The end could happen before the beginning. But the application layer knows not to play that just yet. So it queues it up in its buffer until that time code is reached. So it's not like, oh gee, now everybody's off the internet and it's going by fast. That could be possible, but it could also be it took that one message a long time to get there and all the other messages found a shortcut. Alright? So you're only forced from doing that by what the programmer chose to use. As a developer, you have to decide what you're going to give up with, reliability over performance. But if you're in a really questionable area, you might choose reliability just to make sure that everything gets there. Yeah? So we start the encapsulation process, by adding a header. A UDP header is going to be a lot smaller than a TCP header, hence more efficient, better performance. Earlier I proposed, before I get there, I got to tell you something else. Remember I told you that we're going to have multiple applications probably running concurrently? And we're probably going to have multiple computers on our network using our connection probably concurrently as well. So not only do we gain segmentation as a way of dispersing our messages across several connections, but we also allow multiple people to use the same connection rather simultaneously. Now, I put the word rather simultaneously. It's just like time sharing when it comes to your processor. It happens so fast it looks like your computer's multitasking, which it doesn't really do it. At least the old processors never really multitask. It did one task and the other task rather extremely fast. It looked like it did it at the same time. All right, guys? So likewise, when it comes to networks, most of our connections can't handle parallel connections. That is, concurrent connections at the same time. So what we do is we multiplex the conversation. That is, we take segments from different conversations and interweave them together. So it looks like everybody's using the same network connection at the same time. Clear about that? So by segmentating the data, it also allows for multiple people to use the same connection. Right? So there's no monopolization happening. All right, so earlier I posed a problem. I said that the transport layer is designed to identify the application and the services that are receiving it. But because these segments are going to be traveling all over the internet, different pathways, we need some kind of mechanism that when that message gets to it, it knows what pathway to send it down to. So it ultimately gets to the final destination. That's what this layer is all about. This is called the network layer. It gets its name because when those messages or the segments are being distributed across the network, this layer has got to be used by a particular device to route it along its way. And that device is called a router. So not only do we have protocols to identify each layer, we also have devices. So when you get to about layer 3, you're going to get into specialized devices. Layer 4 and up, probably going to be internal in your computer, into your operating system, into your end device. In fact, when you get into Windows, you'll see the transport layer. There's a protocol installed called TCP/IP. And you can go in there and make some settings, like the flow control, like the segment size. So here we are, layer 3. It's going to take that segment and once again re-encapsulate it. So now we have the segment. We're going to add a header to it. That's for each segment, by the way. When we re-encapsulate it, we're going to call this a packet. What's the difference between a packet and a segment? A packet has information used to identify end devices. The key is identifying end devices. So the sender and the receiver. I before E except after C, is that the rule? I hate the English protocol. That's just crazy. I always misspell receiver. So, that is to say, in this header, there's got to be an addressing mechanism. What addressing mechanism have we learned so far? Or at least explored, I should say. Exactly. Hence, the protocol used in layer 3 is typically IPv4. But it's not the only, and I got to beat this out of you guys because it took me a lot of years myself to convince myself, other protocols do exist. IP is one. We have AppleTalk is another. We have NetBayou is another. We have IPX is another. We have something called connectionless network services. So they go on and on. IP is the most popular. Why? Why is the IP protocol the most popular compared to, let's just throw Apple under the bus. So AppleTalk. Why is IP more popular than AppleTalk? Open. It's an open protocol. And so more people are more willing to adopt that because it costs them any money. So when HP decided to make a network-connected printer, it decided to say, oh, I'm not going to go buy AppleTalk. And at one time, especially in the 80s, you'd have to buy several different interfaces for your printer to get them to connect, or your end device. And so now it's like, you look back at it there, the only thing you're going to see is either a USB port or an Ethernet port. That's it. Nowadays, you could buy these computers without these printers without connecting any wires to it, as long as they agree to the 802.11. So this is the nice thing about openness. If more people start to use it, it starts to become a standard. And if popularity dictates, that's the only thing we're going to learn in this course. But I will put that little fine print. It's not the only one. Okay? If I'm making this point, expect to see it on one of your exams, one of my exams that I make for you. Question? They won't ever do it again. It cost them too much financially. They realized they weren't as powerful as they thought they were, so they had to start developing things that were more accommodating. Yes. Because when they started seeing the popularity of the internet, and by the way, that's the only reason why we got rid of all this, well, not all of it, but most of the proprietary bullshit's been gone because of the iSocket, or the iSoc, the Internet Society. Hosting and making things open and free for the market has caused other companies to say, hey, I want you to use my product. Well, I'm only going to use your product if I can get on Facebook. In fact, isn't that the biggest complaint about going from Android to iPhones or the iOS? What's the biggest thing that Android has going for itself right now? It still plays Flash. Whereas the iOS says, Apple's like sticking it to Adobe saying, nope, got security problems and you're too battery hungry. So we're not going to allow any Flash content through our devices. And it's annoying. It's really annoying. When you're trying to go onto a website in this open free platform and it says, oh, you're using iPad, sorry, tough luck. So people buy Android tablets. So this is that philosophy coming into effect. So the network layer is going to basically set a source IP address and a destination IP address. The source, where it came from, destination, where it's going. The important thing is, in that address is going to be a network address, and that's how routers know where to pass things along. All right, after we get done with the network layer, we go to layer 2. This is my favorite layer out of all of them, folks. Data link layer. Okay, when I say the word link, what are you guys thinking? Give me a basic, bare bones, generic definition of a link. Yeah, it's going to connect two things together, right? All right. Everything up to this point looks like this. If you see that, what's the generic term for that? What would you guys call it? And don't call it binary. But it's what the machine uses to store what? Data. Because what's the definition of a computer? Anything that receives data, processes it, and converts it into information, right? So that means the machine sees it like this. This is data. So if this layer is called the data link layer, it's taking that and linking it to what? The last layer, layer 1, which is known as the physical layer. This is layer 2, is the last layer that the encapsulation process occurs. In fact, when we get done in the layer 2, data link layer, we produce a frame. What is a frame? It is a packet with a header and a trailer. This is the only layer that we add a trailer to the encapsulation process. All the other layers set a header's just fine. Why does this one have a trailer? This is the last time. In fact, this layer has two sublayers. One's called the logical layer, and the other one's called, oh, we're blinking, so I lose this. I hate that. Hopefully it's still recording, but whatever. You guys are watching this video, it probably got cut right here at this point, which is almost just in time. But regardless, this layer has two sublayers. One's called the logical layer, the other one's called the MAC layer, the media access control layer. And it's linking the physical world with the logical world. How does it do that? With things called MAC addresses. See, earlier we talked about IP addresses as identifying the sender and the receiver, the source and the destination. Before that, we talked about port addresses, right? And what were they used for? To identify the application and the service, correct? So these addresses are used for identification. Transport, applications and services. Network, sender, receiver. There's addresses here. We call them physical addresses. What do you guys think they're going to be used for? Along this journey to get from here to there might be several different pathways, several physical connections. Like for me to get from here to my office, I gotta go out of that door, walk across this carpet rug, go up these concrete steps, walk across a tile floor, back on the carpet rug, then to my office. Now, since it's Corning, I really don't care. But if it's at home, I might want to take off my shoes. Right? If I'm walking on tile at my house, I really don't care to take off my shoes. Grab them up, clean it up, done. If I got muddy shoes and I walk on my rug, somebody's going to kick my ass. Right? You see these different physical properties and how it affects behavior? So somebody told me, you see rug, take off your shoes. You see tile, walk on it. Likewise, at this layer right here, there's rules. The protocol that we tend to use in a wired-based network like the one that you guys have right in front of you is the Ethernet protocol, or the Ethernet standard. And in that protocol, they are going to tell me when a frame begins and when a frame ends. And that's why it's important that this layer produces a trailer. Can you guys tell me this wire is actually unplugged now? Are there any zeros and ones on this wire? Why do you say that? It's not plugged in anything? Well, let me tell you, this wire is made of copper. What have we learned about copper? It conducts electricity. It's also susceptible to what we call EMFs. If you guys don't believe there's any zeros and ones on here, when you get home tonight and you're bored, go grab a metal pipe. 6 feet, 10 feet will do. And take this wire, strip the insulation off because you need to get a charge out of this exercise, and wrap it around that metal pipe. And then go find those 600 volt power lines, those big transmission power lines, and drop it underneath it. And hold it for a second. The longer the pipe, the more voltage, the more charge you'll get out of it. We call this induction. You're starting to see this with wireless chargers. We can charge your batteries without any wires. So, once again, are there zeros and ones on this wire? Absolutely. The tree falls in the forest and nobody's around to hear it, it does make a sound. It does make noise, I should say. So, where is it coming from? Our atmosphere. David, question. Yep, detect it. Yeah, exactly. Using the same induction. All right, so, there are zeros and ones on this wire all the time. How do I know those zeros and ones are my data, or they're just bogus signals? How do I know that this is just some random mess? Versus, I'm sending Morse code. This very rarely happens in nature, where it's very systematic. It has a beat, it has a tone, there's timing involved. And you guys could time in if you want, because you know the intervals, right? When I start seeing that, I'm like, wait a minute, that's pretty weird. That I'm getting clap, nothing, clap, nothing, clap. I might get some random crap, but this seems like it's done intentionally. So your interface card perks up. And it says, I know that pattern. This pattern is telling me the beginning of a frame. Now, this pattern goes on for so many seconds. I don't necessarily know when it began, but I do know this. That should end the pattern, right? So anything after that is going to be my data. Now we need a trailer, and that might be something like this. And that ends the transmission. That's how I know to grab a frame, where the frame begins and where it ends. Because once I know the beginning of my frame, I can remove the header. And what do I get when I remove the header in the trailer? I get the packet. I pass it up. Now that I got the packet, I remove the header. And what do I get? And I pass it up. Now I remove that header, and I wait to build the data back up to its entirety, and I pass it back up to the application layer. And that's the communication process. Sorry I ran over. I will see you guys, some of you tomorrow, others of you definitely on Wednesday. You guys take care, watch those videos, and stay tuned.